I'm Takaki from Tokyo City University. Today, my talk, core design on thorium breeder reactor and the strategy for the introduction. My university, because the name of university must be new for you, name was recently changed from Musashi Institute of Technology. It's a Japanese MIT. It was, and the name was changed to Tokyo City University in 2009. We have several campuses in Tokyo and Yokohama, and our university is a private university, but focused on research topics to serve the sustainable development of society. And the key issues include energy, environment. So our university is not so large scale, but we have atomic energy research laboratory in Kanagawa Prefecture. In the laboratory, we had Trigger 2 experimental reactor. It's a very unusual, small private university has experimental reactor. Is not usual, but we did. Did means about 20 years ago, there was a small water leak from the tank. We have to stop the reactor, and the university tried to restart Trigger 2, of course, but because of strong opposition from the neighbors, inhabitants near the laboratory, the university have to give up, restart. And now the all nuclear fuel sent back to United States. So the operation is terminated. But we still have the laboratory, and we are actively doing education in graduate school in a collaboration with Waseda University. It's an excellent private university in Japan. We have common graduate course for nuclear energy. I had worked for TEPCO for 16 years, and all the years are dedicated to FBR development, sodium-cooled FBR development. But after the last 4 years, I was a part-time staff of Tokyo Institute of Technology, and I was able to study on thorium, water-cooled thorium breeder reactor. I worked on this topic with Professor Hiroshi Sekimoto, and as an activity for thorium reactor, thorium utilization, we study on a traveling wave reactor using thorium for power flattening. There is a very interesting findings. In the usual traveling wave reactor, we use depleted uranium or natural uranium, and the wave automatically moves by transmuting uranium to plutonium. But if we use thorium, we can never realize this traveling wave because of the physical properties of thorium. In short, this traveling wave reactor is a kind of ultimate fast reactor with very hard neutron spectrum. And to achieve the high neutron economy with a high eta value. Eta means neutron reproduction factor. But for thorium, for uranium-233 has smaller eta value than plutonium-239. So the neutronic performance is not enough for the traveling wave. Anyway, my today's talk focuses only on water-cooled thorium breeder reactor. These are contents. I'll talk about core design, heavy water-cooled thorium breeder. Before this, I'll talk about the background, then deployment strategy, and the synergic system with uranium-plutonium reactors. The motivation, we started this study in 2005, around 5, yes. And why breeder? This is very obvious, to make full use of nuclear resource to minimize fossil utilization. And this is a common requirement for Japan, China, and other countries. Especially Japan has less natural resource, so having such technically sustainable energy system is key, especially for Japan, and for the sustainable development of the world. And why water and why oxide fuel, solid oxide fuel? Why not liquid? It's based on my 16 years experience dedicated for sodium FBR development. Of course, it's very well-established plant technology with water and established fuel technology with oxide. My major job was sodium-cooled reactor development, but the problem is sodium is not transparent and active with water. So the coolant is a very convenient coolant for maintenance operation. There is a continuity from existing technology. And why thorium? Of course, there are many people already talk about this. Why thorium? One is to diversify fission energy resource. The other is smaller minor accident production. But my concern is not there. My concern is here, breeding potential with negative void coefficient. If you try to design breeder reactor with sodium in a large scale sodium fast breeder reactor, it's very difficult to achieve negative void coefficient. It's almost impossible. If we abandon breeding performance, we can design negative void coefficient sodium reactor. But if we try to achieve both breeding and negative void coefficient, it's very difficult for uranium-plutonium fuel reactor. But thorium, we can do it. By using thorium, we can do it. Other point is no severe energetics during core disruptive accident. Sodium-cooled fast breeder reactor uses a high enriched plutonium, about 20% or more. In case of core disruptive accident, there is a possibility of leak criticality. And once the criticality accident happened, energy released. And for example, Monju is designed to withstand the pressure, withstand the explosion force in case of CDA. But if we increase the capacity of reactor, it becomes more difficult. But by using thorium as a breeder fuel, the enrichment is lower than that of sodium fast reactor. So in case of core disruptive accident, we may prevent energetics. There's such possibility for the thorium breeder reactor. That is why I'm very keen on thorium. This table shows a comparison between past studies and our study. Thorium breeder reactor study has been done in the United States using shipping port sorry, PWR. PWR. Of course, it's a light water. The shipping port PWR demonstrated breeding performance almost equal to 1.0, but the burn-up is very low. And they use very complicated fuel assembly. It's a movable, heterogeneous, very complicated fuel to improve the neutronic performance as a breeder. So it's easy to suppose it's difficult to commercialize. But it has negative void, and yes. And India strongly chasing thorium reactor. And their recent design, advanced heavy water reactor, uses uranium-233. And this reactor is a kind of sustainer as for uranium-233. But they need external supply of plutonium. So in that meaning, the net breeding ratio, net fissile balance is less than 1. So in short, the Th-HWR consume plutonium, but it can sustain uranium-233. The burn-up is like this. And there are another concept, reduced moderated BWR, originally proposed by Hitachi. And now there's a small study activity in UC Berkeley. It's a very, this is a advanced BWR, a kind of advanced BWR. The breeding ratio is more than 1, and the burn-up is 45 gigawatt per ton. But they use actually heterogeneous fuels with blanket. And the most challenging engineering problem is it has very tight pin gap. So the heat removal, summer hydraulic problems have to be confirmed by experiments. The new challenge. And another problem of reduced moderated BWR is shutdown margin. As you know, the BWRs contains bubbles during operation, but in the case of cold shutdown, all bubbles are diminished, and positive reactivity is inserted. To compensate positive such reactivity, we have to prepare a very powerful control rod. So such design is not technically feasible. So that is a problem. And our study uses heavy water. Heavy water uses as a primary coolant in a PWR. And the breeding ratio more than 1, and we achieved very high burn-up with very simple core configuration. It's homogeneous, no heterogeneity, and no blanket. And the pin gap is enough. There's enough gap, and the shutdown margin also enough. So I'd like to told you this in details from now on. And I'd like to show you some findings from our previous study. This graph shows this axis moderator to fuel volume ratio. This is very important parameter to determine the neutron spectrum of the reactor. If we use light water for the thorium reactor, there is a limit line for breeding, like this. The current PWR has are about MFR of 2, so it's not never be a breeder reactor. By reducing MFR, moderator to fuel volume ratio, the spectrum is hardened and the breeding performance is improved. But there is another limit. This is a limit for the negative void reactivity coefficient. And in addition to that, there is another limit. This is a geometrical gap limit for triangular arrangement of fuel pins. We cannot reduce the gap less than 1 millimeter to keep the sufficient heat removal capacity. So there's a limit. So you have to design within this area if we use light water reactor for so the achievable burn up is not so high. So we changed coolant from we plotted the real data getting by from shipping port experiments is here. So our results is consistent with the experimental data. So we investigate the heavy water coolant. Heavy water coolant has very interesting property. This axis shows a wider range of MFR from 0 to 30. By increasing MFR means by softening neutron spectrum, the feasible area for breeding is broadened like this. Because of uranium-233 has good performance in a well-thermalized spectrum. But there also exists a limit around 20 gigawatt day per ton. So it's not so attractive as a commercial reactor. And we turn attention to the smaller MFR area, there's a sharp window towards the higher burn-up. Here is the MFR equal around 1. If we design heavy water cooled reactor with this MFR, there's a possibility to achieve breeding performance and high burn-up. So we focused on our study effort on the heavy water. This shows the neutron spectrum. If the MFR is 20, like today's CANDO reactor has this kind of spectrum. And our reactor has very small MFR, as the spectrum is between 0.5 or 2. Anyway, very similar to sodium-cooled fast breeder reactors. So, let me summarize my past studies results. Design window for thorium breeder is wider for heavy water than light water. Thermal spectrum is not necessarily optimal to achieve breeding capability with high burn-up in case of thorium. You know, every textbook for the reactor physics tells we can design breeder reactor use thermal breeder by using thorium, but it's not wrong, of course. But if we try to achieve high burn-up with breeding capability, thermal spectrum is not suitable. More harder spectrum is better. And lower power density shows better breeding performance or better burn-up, because the protactinium-233 consumes stays 30 with 30 days, 1 month decay half-life, and if we increase the neutron flux, means power density, we lose more neutrons by protactinium-233. So the lower power, lower flux reactor is better in case of thorium. And the heavy water reactor is we design big 3.5 gigawatt thermal power heavy water is feasible to achieve breeding performance with negative void reactivity coefficient and higher burn-up. The core is homogeneous, simple, with large pin gap. And acceptably small heavy metal inventory. It's about, we need 200 of heavy metal for this output. It's rather, it's bigger than the current light water reactor. This is because we employ tight pitch fuel assembly and lower power density. But the core size is similar to today's PWR, because we have more heavy metal, but in a tight arrangement, so the diameter is same. But one problem is by hardening neutron spectrum, first neutron fluence exceeds the limit of the Galois. So we have to consider about this. And one more, generation cost of heavy water cooled thorium breeder is less than that of light water reactor generation cost. Today I don't have time to talk about this, but we made some deep study on the generation cost. And what is interesting is this generation cost is higher than that of Japanese sodium fast reactor, because JAEA, Japan Atomic Energy Agency, officially tells in their report this sodium large-scale fast breeder reactor has very cost-effective. Is very cost-effective. Okay, and this is a core configuration of our heavy water cooled PWR. It uses a hexagonal fuel assembly because of tight pin arrangement. And the fuel assembly is, all fuel assembly is in the same design. Very homogeneous core, 282 fuel assembly, and 96 D2O reflector is surrounded the core, and we equipped 19 control rods. And this 19 control rods design is similar to that of Monju, and the total rod worth is enough for cold shutdown. This is a specification. Yes, this core has very long cycle length, 1,300 days, and 3 batches. So each fuel stays in a reactor about 4,000 days, more than 10 years. It's very simple homogeneous core without blanket. The enrichment of uranium-233 is not so high. Pin gap is enough, which facilitates heat removal. So this core achieves burn-up about 80 gigawatt per ton and breeding more than 1. And as I told before, the problem is cladding material integrity. Evaluated first neutron fluence for this core is these values. this exceeds the limit for the zero because of long cycle length. This is a spectrum of a core. This red and black line shows the spectrum. And this blue line shows the spectrum for sodium-cooled uranium-plutonium fuel FBR. Our core has very similar spectrum with sodium-cooled one. So the other cladding than zircaloy material have to be employed for this core. So we choose silicon carbide because some researchers studies this material as a cladding material recently. So the objective of today's this study is evaluate the core performance diesel-cooled thorium breeder. We name it heavy water Th-HPWR with silicon carbide cladding, and to picture the strategy to introduce this reactor harmonizing with current light water reactor and the future FBR with uranium-plutonium cycle. Okay, this is our analysis method. We use gender library and Slack code and cladding material silicon carbide. Moderator to fuel volume ratio is fixed at 0.6. This graph shows a K effective with burn up for zircaloy core and silicon carbide core. As you see, the silicon carbide core has slightly better K effective. And this figure shows a conversion ratio with burn up. And this also shows silicon carbide is better in terms of conversion. And other performance, for example, burn-up reactivity loss is smaller for silicon carbide, and the control load loss is almost same. Average discharge burn-up almost same. And the fissile inventory ratio means kind of breeding performance is like this. So by changing cladding material to silicon carbide from zircaloy, neutron performances were improved. And this shows a void reactivity coefficient for the zircaloy case. Local void coefficient here, and 9 locations. And there is one location which shows positive coefficient. But by changing cladding material to silicon carbide, all coefficients are negative. And the neutron spectrum is, neutron fluence for the silicon carbide is similar to that of zircaloy, but the limitation is higher. So we can use silicon carbide for this hard spectrum reactor. Okay, deployment strategy. This is current phase. We use uranium fuel in light water reactor, and as I show, we can sustain by using thorium in a heavy water cooled PWR in a breeder phase. But the problem is how to connect this phase and this future phase, because this future phase needs uranium-233. And to prepare uranium-233 in the breeder phase, we consider transition phase. We use plutonium from the current light water reactor spent fuel in a same design pressure heavy water PWR, and to produce uranium-233. So we use same design heavy water PWR in the transition phase, in breeder phase. Just change the fuel, plutonium, thorium fuel, or thorium uranium-233 fuel. We can switch fuel in each phase. And this is the result. If we try to replace 60 gigawatt light water reactor by thorium reactor, the transition phase reactors is introduced by this pace. And this reactor produces uranium-33 for the breeder phase core, and the breeder, thorium breeder, increase like this. In total, blue line, thorium reactor replace all 60 gigawatt light water reactor within 1 century. Of course, for that mass balance calculation, we have to assume some parameters. I assumed first, sorry, this is very complicated figure, but this is a stored spent fuel from light water reactor is here. This blue line, light blue line, I assumed 25,000 tons of spent fuel exist now. This is a value in case of Japan. And I also assumed reprocessing capacity of 800 tons per year reprocessing capacity to reprocess spent fuel. By reprocessing this spent fuel, we can get plutonium for the thorium reactor. Okay, but the stored spent fuel of light water reactor exhausted within a century. After this, we cannot get plutonium anymore. So deployable capacity of thorium reactor depends on plutonium stockpile at the beginning. This is very important. We have to recognize this. Yes, we want to, if we want to construct thorium reactor, we need fissile material. That is why India chasing thorium energy for long years, but they cannot construct thorium reactor because thorium is not suitable to expand nuclear reactor capacity in a short term, because thorium reactor requires fissile materials more than uranium reactors in a first stage. To prepare first core, we need more fissile materials than uranium. So we need such a mass balance calculation. And deployable capacity of thorium reactor depends on light water reactor capacity and reprocessing capacity. I assumed 800 reprocessing capacity, then increase to 1,200, then increase to 1,600 tons per year. This amount of capacity is required to deploy thorium reactor. Okay, and the last one is synergic system with uranium-plutonium reactor. Japanese official nuclear policy is using sodium fast reactor, and minor actinides are burned in the sodium fast breeder reactor. But if we consider using thorium reactor, we can send minor actinide to the thorium breeder reactor. This consumes very efficient, achieves efficient minor actinide transmutation, and thanks to that, better fuel handling due to less heat from minor actinides. And better, if we use thorium critical system, the energy balance is better than using ADS. It's obvious because ADS needs electricity to be operated. And we can realize this based on mature plant technology. And by using thorium in addition to uranium, the energy production is enhanced. Okay, conclusion. Heavy water cooled thorium reactor, heavy water PWR, is feasible to be introduced by using plutonium recovered from spent fuel of current uranium light water reactor while keeping continuity with infrastructure. HPWR can also be operated as sustainable energy supplier and MA transmuter to realize future society with less waste and abundant energy. And this reactor generates this amount of thermal power with long cycle length, with high burnup, with negative void reactivity coefficient all over the core and all through the cycle. This is a list of my papers, and this is the newest one. Thank you for your attention.
Are you sure your simulation is reliable? Because I'm very surprised that with the presence of heavy water, there is no sign of thermal neutrons in the system.
Yes.
There should be some thermal neutrons, especially you have a reflector around with the heavy water. How come there is absolutely no thermal neutrons?
Yes.
Maybe your steps in the simulation are so large that you never capture, you never interact with the heavy water because it's too thin or something like that. But there should be some thermal neutrons in the system.
The reason why this reactor shows this hard neutron spectrum is owing to the small amount of modulator. So I use MFR, modulator to fuel volume ratio, is about 0.6. There are very small amount of heavy water. Heavy water has less performance to modulate neutrons compared to normal water, and the volume ratio is very small. So this spectrum is achieved.
Quick question is, what limits the burn up? Why do you cannot exceed 60 gigawatt day per ton?
Oh, to keep breeding performance. If we give up breeding capability, we can extend burn up more and more. It's a balance, breeding and burn up.